Hey everybody, welcome back. We're going to be doing another lesson in geology. This time we're going to be talking about the geology of mountains. And mountains are absolutely a phenomenal topic in geology. They're also a huge topic, not just because of their size, but because of the amount of information that mountains convey. It's kind of a capstone for a lot of geologists to learn about mountains, especially at an introductory level, because it's in the mountains that we see Earth's story laid out probably the best. This is where you get your igneous rocks, your sedimentary rocks, your metamorphic rocks, all combined into a single package. And then you have your folds, your faults, your joints, you have your glaciation, you can even have your deserts. You've got all kinds of things that are happening. And then you got plate tectonics that explains it all. What's even more amazing about these things is that when we look at these rocks, for example, in these mountains that we see back here, these layers are still visible. While they're tilted, which shows that there's some type of structural change that's happened, they're tilted, and it turns out in this case, these are marine sedimentary rocks. So how in the world do rocks that belong in the ocean wind up in these peaks way up high in these mountains? In fact, the very top peak of Mount Everest, which is at over 29,000 feet, I mean, that's as high as airliners go. Those rocks are marine rocks. It's kind of mind-blowing. The purpose of this lecture is to go through really the origins of mountains, where they come from, what does plate tectonics have to say about them, and the explanation. And one of the things we learned very quickly is that oceans, what's actually happening in the deep ocean, has a very, very strong influence on what happens in the formation of mountains, just like we see right here. So let's go ahead and jump into it, and we're going to basically learn about mountains, their roots, their formations, and what drives them up as high as they are. This is going to be a very comprehensive lecture, but I think you're going to really enjoy it. Anybody who loves mountains and wants to know where they come from, especially mountain belts, is really where we're going to be focusing, not necessarily individual mountains, but on entire mountain chains. I think you're going to really get a lot out of this. So let's go ahead and jump into it. All right, so the very first thing we need to do in our journey to learn about mountains and their origins is to define what a mountain is in the first place. We need to define our terms. And so we're going to define it just the same way that the old English or Oxford English Dictionary would do so. It's a landmass that projects conspicuously above its surroundings and is higher than a hill. We don't want to spend our time worried about the little hills and the little valleys that might be surrounding, a coastal plain or something like that. What we're interested in are large mountain belts, the very large structures that can go for hundreds, perhaps even thousands of miles up and down continents and have a major effect upon the surface of the earth. So we're not going to spend our time worried about single mountains, but just in terms of our definition, we want to make sure that we understand that we're not talking about small stuff. We're talking about big stuff. When we're looking at Castle Crags in California, which is a single mountain within the Klamath Mountain Range, which is a part of a mountain belt that extends hundreds of miles along the coast of the United States. Castle Crags has all the features of a classic mountain that we think of. It has the extremely high the heights. It has the beautiful scenery, the majestic views, and it's obviously a major part of the environment, the geological environment here. And it's telling a clear story. These are beautiful exposed granodiorites. This is the heart of an ancient volcanic system in California. There are three different types of mountain belts characterized by how they formed. And we're going to spend our time dealing with mainly the first two of these and then a little bit in the third one. And the reason why only a little bit in the third one is because it's review, so let's talk about those. So we're going to talk about volcanoes. Now, we've done volcanoes before, but we've talked mainly about what they call their morphology, what they look like, the craters, what the rocks look like that come out. What we haven't really got into is the origin of volcanoes too strongly. So we've talked about the origins of magma and lava. We've talked about the origins of igneous rocks, but not the actual origins of volcanoes. And it turns out plate tectonics gives us a very good explanation. Volcanoes frequently represent some of the largest mountains on planet Earth. The other ones are the collisional mountains. Collisional mountains are some of the highest elevations on planet Earth. They're not necessarily the tallest mountains, but collisional mountains are where we have two land masses sliding into each other and there's no place to go but up. And so that's what they do. Mount Everest is a collisional mountain, for example. And people would say, but isn't that the fact that it has a higher elevation make it taller? Well, Mount Everest starts at a higher level and then goes to an extremely high level, whereas the tallest mountain on planet Earth is Mauna Loa, which starts at the sea floor and then extends above the waterline, above the sea level, and then considerably above that. I believe 13,000 feet or something, memory serves. So you have a much taller mountain in Mauna Loa than you do in Mount Everest, if you measure it from base to top. And then the last group are the fault block mountains, which are extremely important mountains. These are a major landscape former in the western United States, much of Mexico, western Canada, but it also is a major deal throughout Mongolia and other places. So it's an important set of mountains to talk about, but it is also review because we talked about them to some extent in our last discussion on the geology of folds and faults. We talked about fault block mountains as an example of extensional faulting. All right, important term to know right off the bat is orogenesis, which is really can be defined as the origin of mountain belts or the origins of mountains. So orogenesis is the process that collectively produces a mountain belt. An episode of mountain building is called an orogeny. So that's the term that we use, orogeny, oro meaning mountain, geny meaning is coming from genesis, meaning the formation of a mountain. So orogeny is an episode of mountain building. Now, several mountains ranges in particular, the Rocky Mountains immediately come to mind for me, have several orogenies that explain the existence of the mountains there today. So there was the ancestral Rocky Mountains, which are considerably older than the currently uplifting Rocky Mountains that we have today. So we have two tectonic systems operating at different times. So one mountain range, but we have two orogenies that are creating them. Okay, some episodes are ancient and others are young and happening today. So that's the reason why you can have multiple episodes to create a single mountain range. So several orogenies to create a single mountain range. Mountains that display faulted or folded rocks are called compressional mountains. And so here we see a classic, right here an anticline, and then there's a syncline. So here we have an anticline, syncline set. So here's a fold going through a compressional mountain. In fact, the old term for compressional mountains before we realized that faulting was such an important part of that was they were called fold mountains because the folds stood out. They were very easy to identify. And they're known for displaying visual evidence of compressional forces. And this can include metamorphism and some igneous activity. And that metamorphism sometimes leads to the formation of valuable gems that are mined by industry for the purposes of making jewelry or for the purposes of producing aggregates or things that are used in construction. So let's talk about the context of orogenesis, where it seems to be happening and where the orogenies are. So there are young mountain belts on planet Earth where we see current uplift or very recently uplift of the mountains and the formation of these mountain ranges. And then we have old mountain ranges that have not uplifted in a very long time. They're actually being deeply eroded, but they give us the analogs that we need, right? In science, we can't just say this is what we think. We actually have to go and look at examples of where we think this has happened, not only currently, but also in the past, so that we can make comparisons. And that's what a large amount of this lecture is going to be. We're going to go through several different mountain ranges and show how we know about them, what we do know about them, and their origins. So let's look at these. Young mountain belts are all marked in red. So here we have red going from Alaska all the way down the west coast, right through Central America into South America, and all the way down to the tip of South America. These are young mountain belts, less than 100 million years old. These are the famous Andes Mountains. These are the North American Cordillera up here, which extend all the way from Alaska into Mexico. And then we have another belt. And in fact, if we follow this all the way up to Alaska, we come out on the other side and we pick up that young mountain belt over here. Here's, again, these 100-million-year-old mountains, and they extend all the way down into Asia. Here we see the Himalaya. Here we see the Zagros of Iran, the Caucasus, the Alps, and then finally the Atlas Mountains of northwestern Africa. They are well exposed in the country of Morocco. So we see exactly where the young uplifts are. and they form a ribbon pattern. We can see them moving across the planet. When we look at the old mountain belts, the ones that are no longer uplifting and that are actually being deeply eroded, immediately things like the Appalachian Mountains come into play. The Caledonian Belt up here, the Urals, which is located between these two gray areas on the map. We're going to get into what those gray areas are here in a moment, but it's pretty important. So here we see them again. They're like ribbons. The Caledonian is like a ribbon. Again, the Appalachians are like ribbons. And so they don't form these big bulbs in the middle of the continents. They seem to be aggregated along the edges of these gray areas and these yellow areas. So what are these yellow and gray areas? Well, these are called shields and stable platforms. So a stable platform is a shield covered by sedimentary rock. So let's talk about what these things are. It turns out they're both related to something called a craton. So let's talk about cratons, and then we'll derive what we mean by a shield and a stable platform, and then all of a sudden this map will start to make some sense. So what's really crucial about a craton is it turns out that when you look at that former map, it's where the mountains aren't. So cratons, shields, and platforms, let's talk about them. Cratons are the structural hearts of continents. So we tend to think of continents as these things that are moving around and kind of faulting and folding and rifting and doing all kinds of complicated things. But it turns out there's portions of them that are extremely ancient that are, and when I say extremely ancient, over 600 million years old, that would be kind of the youngest part. So a craton is tectonically stable crust composed of ancient, which is to say Precambrian, crystalline, igneous, and metamorphic basement rock. So this is really old stuff. It's not being folded or faulted, and certainly not to the extent that what is happening in the mountain ranges, certainly not to the extent of what's happening in the ocean basins. These are very stable areas. Earthquakes are very, very rare in a tectonic sense. You can get earthquakes for other reasons. And frequently, these are land masses that have just been sitting there exposed to the elements for hundreds of millions of years. And so they tend to be deeply eroded in certain areas. So a deeply eroded craton with a flat terrain, and that flat terrain, by the way, when it's layered off, when it's just completely beveled off, is referred to as a shield. So there's that word coming in. So here we can imagine a craton. So imagine this is a big igneous body or a big metamorphic body, crystalline rocks, hard crystalline rocks. And it's been completely, run over by glaciers, for example, for 600 million years. So it gets penoplaned off. So it gets flattened. And that exposure of that flat surface of those crystalline rocks is referred to as a shield. And so to give you an idea of what that shield might look like, here's a picture of the Canadian shield. Very, very flat area. If you look along in the background here, we do see some exposed granites up here. These are crystalline rocks that are well over, they're Precambrian in age, so they're well over the 600 million year old limit that we're looking for. And in fact, Canada is home to rocks that frequently exceed 1 billion, sometimes 2 billion, and when you go into Greenland, 3 billion years. These are extremely old rocks, very stable place. So here we have a shield and with the cratonic rocks all exposed. Now, the rocks get shed off or they actually settle out in different environments. We're not going to get into those details right now, but once you have the shield exposed, you might have areas that are not exposed, they're covered or layered with sedimentary rocks across the top. Well, they're still sitting on top of a very stable craton, so this is called a platform. So the craton is down there. It's just not scraped so clean that it's a shield. So that's important. So when we come back to that image, which is what we see here, the shields and the stable platforms, so this is where the granites and the crystalline basement rock has all been scraped clean and you can clearly see it. And the gray areas are where the craton exists, but it's covered with sedimentary sequences. So it's down there, it's stable, it's doing what it does exactly the same under the shield, except it's not as visible. Okay, you have to drill down to get down into it. And we'll notice that when we see these areas, we can think of the shields and the platforms as one and the same. And the mountains are along the edges. Even the Appalachian Mountains and the Caledonian Mountains are along the edges. The Ural Mountains are a ribbon moving right between these. We now know that this is a different continent than this over here. This is the Asian continent is here. Here's the European continent, and we're going to get into that. We call it Baltica. But the Eurasian continent came about when these two collided into each other, and the Ural Mountains are right in between. So it was the edges of these two coming together to make the Ural Mountains. And now that the Ural Mountains are no longer at the edge, they're eroding. So orogeny, we've discovered, is concentrated along the edges of cratons. Cratons therefore serve as the structural, or likely serve as the structural buttress against which orogeny occurs. So one of the ideas that we have is that we have these very stable cratons. They are moving around. I mean, don't get me wrong. They're not just sitting there and not moving. They are moving. In fact, India is very definitely moving relative to Asia specifically. But they're so stable that they're not internally rifting or faulting. What they're doing is almost like playing bumper cars, and they're hitting things around them. And it's the edges where all the action seems to be happening. So what is it that it seems to be interacting with most strongly? Well, when we look at the North American Cordillera and the Andes Mountains, we see that there is these huge uplifts of mountains, very famous uplifts of mountains, but it's not running into anything that we can see at the surface. It must be interacting with something happening down in the ocean. So we're going to lead into that here in a moment. That's a little different than what we see over here. The Indian Shield, which is part of the Indian Craton, is actually in fact moving northward. The Angara Shield, which is where Siberia is in Asia, is moving south. And so these two are pinching towards each other, and there's stuff in the middle, and those things that are in the middle are in fact being ramped up and colliding with one another. So even though this whole region appears to be in the middle of the continent, we have to be aware that they're really not in the middle of the cratons. So the cratons in this case are on the outside, and they're smashing things into the middle. It's a fascinating situation. So here we have the oceans, looks like it's doing some type of smashing into the west coast of North and South America, and then here we see the cratons crushing into things. It's going to be a really interesting talk. I think you're going to enjoy what we're about to get into. So probably the best place to get started in our discussion on mountains and the origins of mountains is with volcanic mountains. I think this is a great place because we already have some experience in talking about volcanoes, magma, lava, and igneous rocks, and we've got videos on them already out. And if you haven't seen them, you should probably go and preview them. It'll help you understand some of the stuff that we're going to be talking about in this video. What's really interesting about volcanoes, especially large mountains with volcanoes in them, is that there's not just the plumbing of the volcano, but there's also the folds and the faults and all the structures that go along with it that are all superimposed on top of each other. So in order to understand that, we need to know why those things happen. You know, the Andes Mountains aren't just volcanoes. They're really tall, collisional style kind of mountains as well. And in order to really understand this, we need to understand that the relationship between the craton and the margins of the craton, the stuff off to the side, and the ocean itself. There's a lot of action happening in the ocean, and the biggest place where a lot of action is happening is at subduction zones. Subduction zones produce the largest earthquakes. There's a huge amount of volcanic activity that happens there, and the other thing that we now know from plate tectonics is that subduction zones tend to move around a lot. So there's a lot of movement, there's a lot of action. By comparison with what happens on the cratons, there's a lot of action happening in the seafloor. So subduction zones. Another place where we get volcanic mountains in the middle of the ocean are the mid-ocean ridges, and of course with hot spots. If you're interested in the mid-ocean ridges, which we're not going to be dealing with in this lecture, that's discussed in the seafloor lecture. And then hot spots, of course, is dealt with in our Earth's interior lecture as well as the plate tectonics lecture. So I would like to refer you to those if you have an interest in those ideas. We're going to be talking about the tall mountains on Earth, on the continents, the things that we see and identify as mountains, like Castle Crags, like we mentioned at the beginning of this lecture show. All right, so let's start digging into subduction zones. Subduction zones are, for a long time, were a real anomaly. It took a long time for geologists to kind of put together the whole structure of what was going on. And so we're just going to kind of get into the findings of it, not necessarily how they figured it out, but the findings of it. And when they discovered how big these things were and how majestic they were, they realized that these subduction zones were really parts of mountain belts that extended for thousands of miles. So subduction zones form the roots of most volcanic mountains and island chains. Subduction zones can be divided into 4 parallel regions. And to kind of guide us through this as I go through this list, I have a satellite photo taken of the coast of Sumatra, which is in the Indian Ocean. So here we see the Indian Ocean, here's Sumatra right here, and we have a classic subduction zone situation happening here. So the first thing that we see is item number 1 is going to be the trench, the deep ocean trench. And so here we see that located right here, and I have it labeled as the trench. Next to it is the forearc region and the volcanic arc region. So this is region 2, 3, we'll just kind of say 1, 2, 3, 4. So the forearc and the volcanic arc. So the volcanic arc is right here, where these dots are locating individual volcanoes in Sumatra. And the volcanoes, it turns out, are all in a straight line. They're taking advantage of something called the Sumatran Fault. The magma that is down below, and we'll get into how it gets there and how it rises up there, is taking advantage of the fact that there's this weakness in the crust. It's coming up along that fault and producing volcanoes. And so here we see volcanoes, like here we see Mount Kaba, I believe that's how it's pronounced, by the way, Mount Kaba. This is the photograph taken of this one here. It's clearly a volcano. So this is a volcanic arc that we see here. And between the arc and the trench is the forearc, as in the B4 arc, right? So it's ahead of or between the volcanic arc and the trench. And so here's the forearc region. And then behind the volcanic arc is the back arc basin, or the back arc region. These are standard structures that we see associated with most trenches across the globe. And Sumatra has probably got one of the best examples of where you can see all 4 of these regions well defined and well spread out, or well displayed, I should say. So we're going to kind of focus on this through some cross sections. I hope you enjoy this. So let's go ahead and walk through a subduction zone and put together all these features so that we know why we're talking about this being a mountain range. And the first thing we need to know is, as we're moving in from the trench, where are the features at? What would those features look like? And how would they manifest themselves? So first off, what is the trench? So the trench is created when oceanic lithosphere bends as it descends into the mantle. We talked about this in the plate tectonics lecture that we did way towards the beginning of the video series, that we have a plate, the old ocean crust, in this case it's the Pacific plate, that is subducting underneath the Philippines plate, and it's creating an island arc up above it. And the result is, as it's arching in, you're forming a subduction zone which manifests itself in the form of a trench, which we see right on the surface. The depth of that trench, it turns out, is directly related to the age of the subducting oceanic lithosphere, the crust that's coming down. So at the Mariana Trench, which is the deepest location in the oceans, we also have the deepest trench. And in this location, we have old lithosphere that is old and cold and dense. If it's old, it's cold. That's just kind of one of the rules of the seafloor. The older it is, the denser it is, the older it is, the colder it is. And so because it's older and it's colder and therefore more dense, it tends to sink more easily. And as a consequence, this crust that we see, the subducting crust into the Mariana Trench from the Pacific plate underneath the Philippines plate, is Jurassic in age, which is quite old. And so it subducts at a pretty high angle. So slabs that subduct at a steep angle of greater than 70 degrees, they tend to produce a deep trench. And so that's what we see out in the West Pacific. Challenger Deep in the Mariana Trench is the deepest spot on Earth today. Just to give you an idea how big these features are, it's 35,827 feet, and is also where the oldest oceanic crust on Earth is subducting today. So that's the correlation, right? You get the deepest trench correlated with the oldest crust that is being subducted. Now, by comparison, Mount Everest is 29,029 feet. So you could put Mount Everest into the Mariana Trench at Challenger Deep and still have a mile of water to go. This is a massive feature. And when we look at it, we imagine we take away all the water, we can see what this would look like. Here we see the Pacific plate and those seamounts that are coming in from the Pacific plate. Here's the Mariana Trench access. These are the same seamounts that are being referenced up over here. This plate is being subducted down, and then this, all the way from the bottom, all the way up to the top of the ocean or to sea level, we're talking about a distance of 36,000 feet. That by itself, that hill slope is the largest hill slope on planet Earth. And then you got to go all the way to the top of Guam, which is the island that sits above this. It's actually the island arc that we see forming from the Mariana Trench. That's another 1,300 feet. So we're looking at roughly 37,000 feet of relief, all the way from the Challenger Deep all the way up to the top of Guam. It's just a massive thing. Like I said, it dwarfs what you would see coming from Mount Everest. And Mount Everest is no joke. It's a massive structure. This is just even bigger. And so we're talking about a giant mountain. It's just a mountain that's right along the edge of two subducting plates, or of a subducting plate in a subduction zone. And it's just something that we don't see because it's generally below the oceans, it's below the water. But it is going to interact, it turns out, with the continents, and that's where this gets pretty exciting. So not all trenches are deep, and sometimes there's a subduction zone that is well developed, but there is no trench in the area, or it's very, very difficult to detect. And that is usually the case when you have a young lithosphere that tends to be warm and buoyant. So it doesn't sink as easily. It resists the sinking. I mean, it will go down. It has to generally be forced down, unlike the older, colder stuff, which will just fall down on its own. Younger plates tend to subduct at a shallower angle and produce shallower trenches. And sometimes this is, like I said earlier, if at all. And when this happens, when you have it really shallow, you can create something called flat slab subduction. So flat slab subduction occurs when angles are less than 30 degrees. So instead of it coming straight down, like what we saw at the Mariana Trench, sometimes it can come in and almost go straight horizontal. And when it goes horizontal, then things get really interesting. So under flat slab circumstances, the mantle and lower crust can get bulldozed, giving rise to strong compressional forces. And that's what's being illustrated over here. This is a flat slab subduction of something called the Farallon plate, which was a plate that exists. It still exists. It's actually completely underneath North America. But it was subducting off the west coast, off where Los Angeles, San Diego, San Francisco, all the way up into the Oregon area. All of this was a big subduction zone that shut off when the San Andreas Fault formed. So this big bulldozed area that they're talking about right here is we have this mantle lithosphere, which is underplating. It's just coming straight in and it's scraping along the bottom, and it's bulldozing the material down here, and that bulldozed material is then compressing, putting compressional stress up on the crust up above it, and this is going to drive mountains to be formed up there. So you can get mountains formed through flat slab subduction. You can also completely shut off the volcanic arc, because it turns out the volcanoes have to go through a series of stages. Effectively, it has to create blue schist, and then the blue schist has to convert to eclogite. We're going to talk about this here in a moment. And when we go into flat slab subduction, that transition isn't as cleanly done. And as a consequence, the water that is on that oceanic mantle lithosphere is subducting down. It finds alternative ways to get out. And so things get pretty interesting when that happens, and that's going to be beyond the scope of this class. We're going to be dealing mainly with the issues of what these forces are doing. So this is flat slab subduction. This is the old view, by the way, before the bulldozed idea came in 2018. Prior to that, they used to think there was strong coupling, that basically the underplating subducting slab would effectively grab the slab up above it and then create basically uplift forces in mountains. We now think that it is different. We think that this is probably a little bit more accurate. So once we get past the trench, we're headed towards the volcanic arc, there's the forearc region. So here we see the trench. And that's what we're seeing here, the subduction zone right here. Here's the arc, and between here and here, where the trench trough is the forearc region. So the forearc region is the area between the trench and the volcanic arc, and it includes something called the accretionary prism, if it is present. Now, I've talked about the accretionary prism in subduction zones previously, but we're going to rehash this a little bit right now because it's extremely important. So at many trenches, the subducting oceanic slab can have some of its marine sediments continually scraped off and added to the overlying plate. We call this accretion as the rest of the slab descends into the trench. So imagine as something is subducting down, the overriding plate, the one that is not going down, is just scraping everything off for the one that is going down. And that's what we're seeing here, is the sediments that have accumulated on the sea floor are being scraped off and then added across the trench to the other plate. So this is material that used to be on the subducting plate is now been transferred over to the overriding plate. That's called an accretionary prism. And the way that's accommodated is through a series of thrust faults. So thrust faults within this accretionary prism can force these sediments to emerge above sea level, forming a series of islands or hills and form the leading edge of a four-arc basin. So here we see these fault splays coming in, and you would imagine that as you're pushing in this direction here, these faults would be moving in the opposite direction. You know, if you come this way, it's all relative, right? So if you come this way, this one's going down, but this one here is also coming up. So effectively, this whole thing, the subduction zone, looks just like a giant thrust fault. And so we're seeing thrust faults here, including what we call little back thrusts. And these are the ones that go back in the opposite direction. So it can get really complicated in here. The main thing that you need to know is you're transferring a huge amount of sediment from the subducting plate to the overriding plate, and it piles up between the volcano and the trench. Okay, so now that we've defined what an accretionary prism is and how it operates, it's kind of that stack of sediment sitting on top of the subduction zone right next to the trench. We can put together a little cross-section of the entire area. So this would be a cross-section, in this case, of the Sumatran subduction zone, where we have the oceanic crust coming in. It's hitting the outer arc, the four-arc ridge that we see here, which is the subduction complex, the accretionary prism that we see here. And then behind there is a four-arc basin. So located between the volcanic arc and accretionary prism, the four-arc basin accumulates thick sediment sequences derived from both sources. So in other words, it's getting sediments that are eroding from off of this outer arc, four-arc ridge, and the actual volcanoes that we see back here. These will be producing large amounts of sediment. The interaction between the overriding and underthrusting plates in the four-arc regions have shown to evolve strong coupling mechanisms which result in massive earthquakes. The largest earthquakes ever recorded occur right in this region right here, right where the subducting slab is going right underneath the accretionary prism and starting to move into the mantle. So it's pretty incredible. In terms of the way that these thrust faults can actually cause the accretionary wedge to push up even above sea level, like what we're seeing here in Sumatra. Let's go back to that satellite photo we saw earlier. And I wanted you to see that. That's what these islands are here. These islands here are the accretionary prism that has been pushed up along a series of thrust faults, very large thrust faults, that are accommodating this whole system on the four-arc region. And then right between here and the volcanic arc, this is that basin, that four-arc basin that we are showing right here. This big unit of sediment. So we have ocean with four-arc basin right in front of it, and then here we have the accretionary prism. And again, these are areas that produce massive earthquakes. Now there's a very important reaction that is happening as we go into the trench underneath this accretionary prism and down into the mantle, and it's a metamorphic reaction, and it's extremely important that we discuss it because we need to figure out how water is getting down into the mantle and creating the volcanoes in the first place. All right, so in order to be able to discuss this, we need to talk about blue schist. Blue schist is something that is formed during subduction cycles. So during subduction, elevated pressures and temperatures beneath the accretionary prism force over 80% of the seawater out of the subducting rocks via marine cold seeps. In other words, let's go back to this image here. As this oceanic crust, that blue line there being sea level, there's a bunch of water up here, the sea, right? The ocean is there. And so as the oceanic crust is subducting, it's taking water with it. There's, little hairline fractures and faults and crevices and fissures, and there's water that's being carried down. But as it gets underneath the subduction complex, and beneath the accretionary prism, I should say, the pressures get so large that a large amount of that water gets driven out. It's almost like squeezing a sponge. About 80% of it gets driven out. And as we go through and put it under greater pressure and greater heat, you would expect more of that water to get expelled. But it doesn't. It gets held on to. And that's what this reaction is all about. It's the blue schist facies transition that seems to happen. So the water that remains is then absorbed by hydration reaction. So there's some chemistry that starts to happen that form blue schist facies metamorphic rocks. So imagine a subducting slab. An oceanic slab is going to be made out of basalt. It's going to have some seawater with it, and it's going to be at about 2 degrees Celsius. Once it gets to about 200 degrees Celsius and the pressure is higher, so this is relatively low temperature, by the way, but it's very high pressure. The combination of these two materials, the basalt plus the water, will start to produce blue schist, which you can see I've got it written right in here. So we got blue schist. This is a garnet-bearing blue schist. Some of the minerals that are in blue schist that color it that blue color is glaucophane. And when we look at the chemical formula of glaucophane, it includes OH, which is hydroxyl, which you can just think of as being water. Just think of it as water. It's a little more sophisticated than that. And then the other mineral is lawsonite, which does have H2O in it. It's not in some type of modified hydroxyl form. So this is explicitly water. So these two minerals form, and what happens is it locks in that water while the pressure continues to increase, the temperatures continue to increase to about 500 degrees Celsius. Above 500 degrees Celsius and at depths of about 50 to 70 kilometers, blue schist rocks will metamorphose to something called an eclogite. Eclogites are pictured right here. This is a beautiful eclogite. So the blue schist to eclogite transition is a dehydration metamorphic reaction that releases water into the mantle. So the water comes into here and they form a single rock, and then when the eclogite forms, it expels the water back out. So it's a dehydration reaction. So the water goes into the rock at 200 degrees Celsius and back out at about 500 degrees Celsius. Why is that important? Well, because when we look at the origins of volcanoes, we recognize from our earliest lectures that in order to create a volcano, and we can actually tell from the gases coming out, there's a large amount of water involved. So the water is getting in there. We know from special tests that we can do that the water is derived from the oceans. So it's an important transition for us to understand. So the volcanic arcs are derived from this. So the subducting slab metamorphoses to eclogite, which in turn liberates water, which in turn partially melts the overlying mantle wedge. So that's a new term. I've never brought up the term mantle wedge before, so we need to describe that and discuss what we mean by that. So the mantle wedge is the mantle located above the subducting lithosphere. So here we see the subducting oceanic lithosphere. I wrote in the word blue schist here, so it turns into blue schist here. Here it's eclogite, so between here and here the water is coming out. That water is helping melt the rock above it. Remember that water is a flux and it lowers the melting point of rock, so the solid rocks of the mantle suddenly become magma. So we see that happening here, that transition. That wedge that we're describing is this right here. See this wedge right here? Almost looks like a point. That's what they call the mantle wedge. And so the water is coming in here at the trench and it's being expelled at the transition between blue schist and eclogites, creating this melt, and that melt is then rising up and forming the volcanic arcs. So it's the water that's actually responsible for this. Remember, the mantle by itself without the water won't melt. It's under too high of a pressure. It's the flux will drop that melting point, create the magma, and drive it to the surface. So melt migrates upward through the overlying oceanic lithosphere and forms a volcanic island arc, or what we also call an island arc. So this is how you form an island arc. So here we have oceanic lithosphere being subducted beneath oceanic lithosphere. So you're going to create islands. When the melt migrates through a continental lithosphere, a continental volcanic arc is formed. So if we have a continent, let's imagine we're off the coast of Argentina, or I'm sorry, Chile in this case. Argentina is a little bit to the east of there. But in Chile, we would see the subduction happening. That transition occurs where the water is coming off and it's already underneath the continent. So you're creating a totally different volcanic arc, in this case on the continent itself. Okay. All right, the last portion of a subduction zone that we need to familiarize ourselves with is the back arc region. And the back arc region can be very interesting. Sometimes it's just kind of a passive area where a lot of sediment can be accumulated, and other times some really wild stuff can happen out there. So we have some interesting text here. Let's go ahead and read this. So the back arc region is located on the side of the volcanic arc opposite the trench. So here we see the volcanic arc. Here's the trench. So the opposite side is right over here, the back arc basin. Can be a passive basin that accumulates pyroclastic material and eroded sediments. In other words, it could just be a place behind the volcanoes where a large amount of that volcanic sediment, the stuff that's washing off the volcanoes, is washing down into a basin. But paradoxically, we've discovered that many back arc basins experience tensional tectonics. If you remember, tensional means extension, pulling apart, right? That's a little strange considering the fact that right over here, we see a huge amount of compression. These are thrust faults. This is moving in this direction. This is moving in this direction. So it's kind of a paradox why you would see tensional stress over here. And so we have some ideas about what's going on. We have some parameters, and we want to talk about that really quickly because it does result in some very interesting landforms on planet Earth. All right, so how do you get extension in the back arc region? So one of the things that we've discovered is that when the subducting plate is old, in other words, if this is a really old plate that we see here in this diagram, so here we see the subduction zone, here's the trench, the subduction is going in this way, the plate may sink vertically as it descends along an angled path. In other words, it can fall straight down. So this causes the trench to roll back away from the overlying plate. In other words, we have this situation here where this subduction is happening. It's actually moving downwards, almost like you're peeling. I frequently use the analogy of a Band-Aid or some type of bandage or tape or something to the bottom of the subduction zone. As you pull it down, what it does is it pulls the whole thing back. And so this is referred to as rollback. So we're rolling back this subducting plate. And so over time, here we see the trench. The trench actually moves to, in this case, to the left. So it was originally here. We come down here. It's no longer there. It's now off to the left. Over the next frame, it's even further to left. And what's happening is the material over here to the right isn't moving, or if it's moving away from the trench, and it's extending. And it's actually creating extension and eventually a back arc basin. So you can actually rift things in an area where paradoxically you have things being shoved underneath other things. So that's a very strange paradox. Our research on this is active right now. And the most recent research indicates that tension and thinning may initiate seafloor spreading, enlarging the back arc basin if the following conditions are met. So in other words, it doesn't always happen, but when these things are met, you may create extension and even create a huge back arc basin. So if the subducting rocks are over 55 million years old, so that means that they're going to be cold, they're going to be dense. In other words, this thing has the very high likelihood that it's going to preferentially go into the mantle rather than be forced into the mantle. It's going to fall into the mantle. Okay. And in doing so, by the way, we refer to, I should have actually mentioned this earlier, as we pull down on this, the mantle has to rush in to fill that hole, and that's referred to as mantle suction. So it's kind of an interesting, or slab suction, I'm sorry. So as the slab is moving in this direction, it's sucking the mantle wedge back behind it. And so that can cause some of the extension. So anyway, just wanted to bring that up as a side note. So subducting rocks over 55 million years old, so they're going to be cold, they're going to be old. The subduction angle has to be at an angle of 30 degrees or more. In other words, it has to be kind of hanging there. It can't be flat slab. And the overriding plate is moving away from the subduction zone. In other words, this plate here has to be moving in a direction away from the subduction zone. So this is moving to the right relative to this subduction zone. And so that's what we see here. Even though it's not moving, the subduction zone is moving relative to it, to the left. And so that creates a zone of thinning and extension. So it's really complicated, but the result is that you can get some pretty profound land features, like the islands of Japan are believed to have been formed in this way. So here we see Japan. Japanese rocks are believed to have formed originally along the coast of what today would be known as China. And we have a series of subduction zones here, one on the Philippine plate, one on the Pacific plate, and that we believe that these subduction zones have rolled back. These are very, very old plates, especially the Pacific plate, has rolled back. And as it has rolled back, that has initiated extension between Japan and China and rafted Japan off of the continent. Now, did it raft everything off? No, because Korea is still a peninsula. But we believe this portion here was originally tucked up right along in here. So Korea and Japan were probably one continuous landmass at one point, located right in here. It's really interesting what can happen. Okay, so now that we've gone over subduction zones, we need to connect that to mountain building. And so it turns out that subduction zones provide the plate tectonic context for the formation of mountains, especially their roots. It's not an accident that where subduction zones exist, where trenches exist, you also happen to have belts of parallel, very tall mountains, usually volcanic. There are two different types of subduction zones. We've talked about them already, but I just want to do a quick review because we're going to do a couple of slides on them here in a moment. Volcanic island arcs, which form when the oceanic lithosphere subducts beneath other oceanic lithosphere. And then there's the continental, what we also call the Andean. It's named after the Andes Mountains. Andean volcanic arcs, which form when oceanic lithosphere subducts beneath continental lithosphere. So in other words, where the oceans are going beneath continents. And so subduction zones accommodate plate motions and allow oceans to close and collisions to occur. Think about that. I mean, it makes sense, right? If you have continents that are moving around in a plate tectonic format on the surface of the Earth, then the ocean basin between it needs to be able to open and close. And the way that you can close a basin is by having subduction, right? There has to be somewhere for that oceanic lithosphere to go. We've already talked about how to create it. As you expand them apart, you get rifting and then you form oceanic crust in that way. But in this way, you can move continents very large distances. And in fact, you can move them at a fairly, geologically speaking, a very quick rate across the surface of the Earth. Here we see a couple of volcanoes, a couple of examples of volcanic island arcs. Volcanics, this is in Vanuatu, which is in the West Pacific, and then the Andean volcanoes and hot springs. These are the volcanoes and hot springs down here. The volcanic system is right up over here. The Andes are extremely tall. These are extremely beautiful mountains, but when I talk about tall mountains, you should be thinking of the Andes as being amongst the tallest. It's right, it's not quite as tall as the Andes, or I'm sorry, the Himalaya, which are formed in a slightly different way, but these are extremely tall mountains. Very volcanic as well. All right, so now let's dive in a little bit into island arc type mountain building. So we're talking about the mountains that form in island arcs. So we've got the subduction zones, so we know what the roots look like. So island arc type mountain building results from the steady subduction of oceanic lithosphere. I mean, you're compressing the ocean into the continent, or I'm sorry, not into the continent, into another oceanic lithosphere, and you're going to ramp up mountains. Continued growth can result in topography consisting of parallel belts of igneous and metamorphic rocks. This is just one phase in the development of mountain belts. And we'll go into those other phases, when things actually close up in an ocean basin. But a really simple and easy explanation or example would be Japan. So here we see the Pacific Plate. This trench right here is the one that eventually becomes the Mariana Trench. In fact, the Challenger Deep is just over here, right off this edge. And here we see the Philippines plate right here. And so we have subduction happening here, subduction happening here. This is a much deeper and older crust, the Pacific, than the Philippine. And so we have the rollback that seems to be happening, the extension of this basin. And of course, here is the island arc of Japan. And that volcanic island arc is extremely active. There's over 100 active volcanoes, but it also has very tall mountains, just like this one. And I'll go ahead and try to pronounce it. I think it's pronounced Mount Hotokadake. Hotokadake. Not trying to get it wrong, but I believe that's how it's pronounced or something along those lines. They're beautiful mountains in Japan. They're actually the focal point of a lot of artwork that comes out of Japanese heritage and Japanese culture. And so these mountains are beautiful. These are largely the mountain range that are in the western part of Japan. So when we come back over here, many of the active volcanoes are around here in the eastern part of Japan, but these mountains that I'm referring to are in the western part. There's metamorphic rocks there, there's igneous rocks there, and they're beautiful. They're absolutely stunning features. Okay, so now that we've talked about island arcs and the beautiful mountains that those can form, let's get into the next stage. Let's talk about Andean type mountain building. This is where there's a slightly different plate tectonics setup. In this case, subduction beneath the continent occurs rather than oceanic lithosphere. And this is associated with long-lasting magmatic activity and crustal thickening on planet Earth. And so we see this in the Andes Mountains, which is what it's named for. In fact, we say this right here, exemplified by the Andes Mountains. But we also see it in the Sierra Nevada of California, and we see it, in fact, in a lot of mountain chains across the planet. It starts, or what we believe, starts with the continental margin. I will say that these are the best studied, best understood types of mountains on planet Earth so far. There's great examples, and it turns out people live very close to great examples. So it's very easy for scientists to go out from their homes and study these rocks. The Sierra Nevada, for example, of California being a great example of this. If we start with the original phase here, we got continental lithosphere. Very, very thick crust. It extends all the way down to the asthenosphere. And here's that very, very thin oceanic crust. This is actually drawn to scale. And on top of it is a continental shelf right along the edge here. So that's our passive continental margin setup that we've been discussing since pretty much the beginning of class. And it forms this thick platform of shallow water sedimentary rocks. And what will happen is if the oceanic lithosphere is dense enough to sink and a compressional force starts to set up on it, you can in fact initiate a subduction zone here. And so what we could do is take this passive margin where nothing is happening and convert it into an active margin. Take this edge and shove it down underneath the continent here. And so once you subduct that oceanic lithosphere, what used to be the continental shelf now becomes, at least along the leading edge of it, it becomes the accretionary wedge or the accretionary prism, and then right along the outer edge here, you'll eventually develop a trench. Here's our fore-arc basin, here's our back arc basin. And so we're starting to develop, right in the very early stages, the structural shape of the fore-arc, the back arc, the volcanics, everything that we see with subduction zones that we see associated with islands. So there's similarities, but there's also important differences. So when we're talking about Andean mountains and mountain building events, it turns out that just like what we see in standard subduction zones in the oceanic crust, as the crustal rocks descend, water and volatiles are driven from the crustal rocks. We've talked about this happening also with the oceanics. These volatiles trigger the partial melting of ultramafic peridotite. So peridotite is the rocks that are in the mantle wedge, which I didn't mention that rock type earlier, but we have, again, eclogites that are dewatering, expelling that water into the ultramafic peridotite, which is here in the mantle wedge, and it generates mafic primary magmas, which rise buoyantly. In other words, these things they're hot, they're fluid, they rise, they're less dense. And so as they move up, they create what they call primary magma. So you get partial melting, and they just kind of sit at different positions within the crust as they rise up into the continental lithosphere. And what this does is it creates something called the formation of a batholith. And we talked about batholiths a little bit earlier on in the class when we talked about igneous rocks, but this is where you get them. So what happens is that thick continental crust impedes the ascent of magma. It doesn't just rise up very, very easily. In fact, in island arcs, it rises much easier than it does in the continental situation, the Andean type mountain belts. Most magma, in fact, crystallizes underground as massive plutons called batholiths. This is where you get your big granite bodies forming. And eventually uplift and erosion expose the batholiths. And we're going to get into a classic example of this in California here in a moment. And batholiths typically range from diorites to granites. So instead of having basalts like what we see in Vanuatu, we see rhyolites, we see diorites, we see granites, we see dacite, things like this. And of course, in the volcanic phases, we actually see andesite, and we see all the rocks, the pyroclastic rocks that are associated with andesitic eruptions. So it's a pretty incredible series of events that happen. You get the magma mixing and all the changes that happen, the differential crystallization of the magma chambers, and it's amazing what you start to see. Great examples of Sierra Nevada in California. So this is a geologic map of California. The Sierra Nevada, the Coast Ranges, and the Great Valley are here. So here's the Sierra Nevada batholith. So these are crystalline rocks. Think of them as granites, granodiorites, diorites, these types of things. In fact, there's even areas in here that are younger volcanics that are more basaltic in nature. Then we have volcanic rocks. These are actually associated with a different volcanic system that is happening right now, right off the coast. This, in fact, here's just to give you a little context. This is the San Andreas Fault right here, but at one point off the coast here was a subduction zone. The San Andreas Fault has replaced that subduction zone, and so there was subduction happening here, and we see the emplacement of this batholith, these granites, which were originally the hearts right in here, these original volcanic hearts of these ancient magma chambers that are now emplaced along here. So these used to be volcanics. This up here, this is where the San Andreas Fault runs offshore, and it actually ends in, there's the Juan de Fuca Ridge and the Cascadia subduction zone. So this is related to a subduction zone that is happening over here, and this is young volcanic rocks up to the north. But when we look here again at those parallel structures, here we see the batholiths, so here are the volcanoes. The Great Valley, which is this big depression, Bakersfield, California, Fresno's in here, Sacramento's in here. The Great Valley is the Forearc Basin. And then the Coast Ranges over here is, in a lot of ways, the accretionary prism. So when we look at this over here, it's this, the accretionary wedge, Forearc Basin, and here's the continental volcanic arc. And then, of course, behind there would be, theoretically, the potential for a back arc basin. Okay, so now we've gone over where subduction is creating mountains itself. Now what happens when the basins get so close, they get so pinched that the continents actually collide, they actually run into each other? When that happens, you get magic. Some really interesting mountains start to form because continents don't subduct. They run into each other, they pile into each other, and folding and faulting and all the great stuff that starts to happen, all the magic that we see in plate tectonics really starts to shine when we get into when continents collide with one another. These are named after, by the way, these types of mountains are referred to as alpine type mountain building. They're named for the Alps where this was first recognized. Two continental masses collide. It's also extremely well studied. The zone where two continents collide is called a suture. So here we have continental crust, here's continental crust, and here we see a suture that is developed here where on one side of the suture is this continental crust all smashed together, and on the other side of the suture is this continental crust all smashed together. We can get really complicated very quickly. Typically contains slivers of oceanic lithosphere. Remember, we call those little slivers of oceanic lithosphere ophiolites. So ophiolites are fragments of oceanic crust. Here we might see a slice of it here, a slice of it here. This is stuff that didn't subduct. It just got accreted, transferred to the other side, and became part of the accretionary prism. It may also include these things called accreted terrains. We're going to get into accreted terrains in a little bit. In fact, when we get into the Cordillera of North America, this becomes a major issue. Most compressional mountains exhibit the deformation of a thick sequence of sedimentary rocks called a fold and thrust belt. So there's folding, there's thrust faults, there's all the stuff associated with the compression of continents all in one mountain belt. It's a lot of stuff going on in mountains. And we're going to dig into three primary examples. We're going to start off with the Himalaya, and then we're going to transfer ourselves from the Himalaya to the Appalachian Mountains. And the Appalachian Mountains are an example of Himalayan tectonics, but it's eroded. So now we can actually look deep inside of the mountains and learn what we think might be happening in the roots of the Himalayan mountains. And then last, we'll get into the North American Cordillera, the beautiful terrains that we see there, including Castle Crags, which I showed you at the very beginning of this very show. All right, so let's start talking about our very first example of a collisional mountain belt, the Himalaya. You can't talk about mountains and not talk about the Himalayan mountains, and these are the kings of continental collisions. And we're going to show you some great images here. But let's get into the origins. So the Himalaya formed, the Himalayas, actually, sometimes I'll refer to it as Himalayas, and sometimes as the Himalaya or the Himalaya. I go between the three of them. But the collision of these mountains, the uplift of these mountains, began about 30 to 50 million years ago. And there's different ways that we know that. There's sedimentary basins that formed at the same time as the collision occurred. We know the age of those sediments that were deposited into those basins. But that collision began between 30 and 50 million years ago. In India collided with Asia following the subduction of the oceanic lithosphere. And of course, India didn't hit it all at once. It hit it at one point, and then it kind of spread along the subduction zone. And that collision then started uplifting the mountains at different stages at different times. So effectively, here we see India. India is moving, this continental crust with its associated lithosphere is moving towards Asia. And Asia had a continental volcanic arc. This is an Andean style arc, the ones that we just talked about. These are already really big, tall mountains, large volcanoes. There's a developing accretionary wedge or prism that's happening here, and the subduction is happening. And then eventually, India collides with the Eurasian plate. And so that's going to shut off the volcano because there's no more subduction that's happening here. Presumably the oceanic lithosphere has broken off or is dangling down somewhere down beneath, but it's certainly not subducting and carrying water down into the system anymore. So it's not producing any more volcanoes. We have a huge amount of crust. We have the Indian Australian plate, which is now underplating in part. It's not subducting, it's underplating. In other words, it's gone down and now they're sitting on top of each other, the Eurasian plate. And so behind this, we have our Tibetan plateau that has risen up. Here's the suture, presumably right here. This is one interpretation. The Himalaya are piled up here. What the old accretionary prism that used to be here is now the Himalayan mountains. All those rocks that are now thrust up into the top of these hills, the top of these very, very tall mountains. Hills is an understatement. These are giant structures. The Tibetan plateau is raised to extremely high levels. We're talking very high elevation. So how did this happen? How did India do this? Well, effectively, as Pangaea fragmented, India moved rapidly northwards. I mean, imagine that once Pangaea, which means all land, remember this is Alfred Wegener's idea, that when the continents separated from their last supercontinent, India, almost like a billiard ball, broke off and started rocketing up in a totally different direction from the rest of the continents. Most of the rest of the continents started drifting away from each other, but India rafted off of Africa, down all the way down by South Africa, where Madagascar is in that vicinity, and started moving upwards very rapidly and collided with Asia in very, very quick period of time geologically. And it docked into it. It's indenting it. And so that lifted up the mountains. It created the plateau behind it. This is a massive structure. And there's some interesting stuff still happening there. In fact, India is still moving forward, northward, I should say, today. So here we see these arrows. India is moving to the north. If we were to put GPS measurements on the Himalayan mountain range at these locations, it turns out the Himalaya are still being pressed into. India is moving forward despite the fact it's run into Asia. The crust is shortening and thickening, accommodating some of this movement. So there's a place where this can happen, but not all of it. You can't stack it all into the mountains. The mountains can stack only so high, and then eventually other things start to happen. So much of the remaining penetration into Asia caused lateral displacement of large blocks of the Asian crust by escape tectonics. That's what these faults are here. Notice these large faults here. Here's a large left lateral fault. Here's a huge right lateral fault. Here's a huge left lateral fault. And effectively, as India is moving and indenting and docking itself into Asia and lifting up the Himalayan mountains, the rest of China and Mongolia in part are trying to get out of the way. It's almost like it's being pushed out of the way while India continues to push in. And what's really interesting, we brought up this issue earlier, the thick cold slab, that's to say the craton of India has stayed essentially intact. It hasn't deformed. It's still pushing forwards. That's this right here. So here's the craton. And as the craton pushes forward, it slams these mountains up. The mountains have no choice. They have to form. And the rest of this area here, there's a craton up here, but in the middle here, there's a lot of terrains and things like this. We'll get into what terrains are. Effectively, stuff that doesn't have the ability to resist a moving craton. So as the craton moves, this stuff has to move out of the way or rise up, and it's all being accommodated. It's absolutely impressive. And when this happens, you can get very tall mountains. In fact, here are two of the tallest mountains on planet Earth. Mount Everest at 29 feet, which is about 8848 meters. And K2, which stands for Karakoram. Karakoram 2, which is at 28,248 feet, which is 8,610 meters. So while these are the two tallest peaks, there's about a 750-foot difference between the two of them. When we come to Mount Everest, there's marine rocks up there. And now you know why they're up there. You almost kind of would be surprised if they weren't. So this is collisional belt. These are limestone rocks that are being assimilated into the collision zone of what used to be an ocean between India and Asia. That ocean basin is in part now up in the mountains. Where's Mount Everest and K2 relative to each other? Well, this map over here shows us. Here's India. Here's the Indian craton. K2 is located up approximately where this arrow is pointed. It's actually about right here. And Mount Everest is located right in this vicinity right here. I think it's actually right here where it's marked by this arrow. The other red zones in here are the other top 10 tallest peaks in the area. And you can notice they're all clustered. So the tallest peaks on planet Earth, almost all of them are in the Himalayan mountains. These are just massive, massive mountains. All right, so now that we've finished our little discussion of the magnificent Himalayan mountains, let's move over into the Appalachians. The Appalachian Mountains are of similar origins to the British Isles, Scandinavia, Northwest Africa, and Greenland. They formed from three main orogenic events, three separate definable orogenic events. And we'll show you some of those orogenic events and how we know that. That culminated with the formation of Pangaea. So like India came from the separation of Pangaea, this is how Pangaea came together. And we have different names for these orogenies. There's the Tectonic, the Akkadian, and the Alleghenian orogenies. And so this is what the Appalachian Mountains look like. They're very old, they're very eroded, but we think this is the plate tectonic setting for the creation of the Appalachian Mountains. So North America was here. The tectonic volcanic island arc was located here. Here we see the subduction zone with a trench and something that we call the Iapetus Ocean. This is not the Atlantic Ocean of today. This is the Iapetus Ocean. And behind the volcanic arc that we see here would have been Avalonia, which was a microcontinent. And we believe that between Avalonia, this microcontinent, which is, think of a microcontinent as a small, it's not like Africa. We're talking about something more like Madagascar, probably a little larger. So the Avalonian microcontinent, and then behind that is the Rheic Ocean. This is not to scale, obviously. The Rheic Ocean was probably much, much larger, as was the Iapetus Ocean. And then behind that was Africa. So Africa is actually moving towards North America, but it has these island arcs, this island arc located here in the way, and also this microcontinent, which is also going to get pinched in between these two. So that's a very important thing to bring up because we're going to wind up looking at terrains where this happens a lot when we get into the Cordillera. We have granites there, so it shows that we've got volcanoes that were happening at the time. So this is a really, really amazing mountain range. and it's very beautiful and it's very eroded. So let's start going through these step by step. So the Appalachians started with the Tectonic orogeny. That's the very first one. So here again is the Tectonic volcanic island arc. We know that it's a volcanic island arc that was located east of North America because it was then thrust. There was a big thrust fault. We can actually map that thrust fault. And it was thrusted over onto the continental block 450 million years ago. We know that because we have those rocks right here. They're of Ordovician age. They're very, very ancient. The volcanic rocks and marine sedimentary rocks were then metamorphosed and are now exposed in New York. Shortly thereafter, we actually have these Silurian Devonian rocks in there. Notice that these rocks here, and I put these in the direction of the beds, are not the same as the rocks above it. So there's an angular unconformity that exists between these. These rocks are of a different orientation. And whenever you have rocks that go from like this to any other orientation, you usually have mountain building. So we have mountain building, something that folds these rocks or tilts these up, and then something that erodes them flat. And then we have these new rocks, which presumably would have been layered flat in the marine environment, the oceanic environment. And then those have since been tilted by subsequent orogenies. So this is an amazing angular unconformity. This is actually a geologist field notebook. So it's a very famous place for students and geologists to go and visit on field trips. So once that has happened, and we have this the Tectonic orogeny that's happened, then we have the continued closing of the ocean basin, and the microcontinent is eventually going to collide with North America. So here we see the Acadian orogeny. And so here's the Rheic Ocean. It's also frequently called the ancestral Atlantic, but we're going to call it the Rheic Ocean. You know, it's the same thing that we see over here. It's this. So Avalonia, this microcontinent, is going to collide in during the Acadian orogeny. And during this time, we get thrust faults and metamorphism and granite intrusions. That shows, the fact that we have granite shows that we have subduction happening underneath North America. So these granites and that batholith would have been intruded right into this location here. And substantially added to the width of North America. So this would have come in, it would have docked into the side of North America, and then once it had collided with North America, a new subduction zone would have set up, and the Acadian orogeny would have been intruded with all that volcanism. Here's a syncline related to the Acadian collision. It's not directly part of the Acadian collision, but this is one of the best photographs I could find. This is in the British Isles, showing a nice syncline, showing that there's tremendous compression happening in the area at this time. The last stage is going to be the Alleghenian orogeny. This is where you really get two continents. Just like India colliding with Asia and forcing up these giant mountains, we have the Alleghenian orogeny. This is where Africa is colliding with North America at 250 to 300 million years ago. The material that was displaced from Africa is 250 kilometers inland on North America. So African geology has been transferred along structures all the way into North America, 250 kilometers. That's a long way. And so we can imagine here we see the Tectonic, the Acadian, and then here we see the Alleghenian orogeny, these two large masses, this giant mountain range that would have been uplifted. Here's North America, here's Africa. And then eventually what would have happened is Pangaea breaks up. And in this area, it started breaking up about 180 million years ago. Now, when it broke up, it didn't break up in the middle of these mountains. It didn't take advantage of this suture. In fact, what it did was it left the mountains behind and it opened up somewhere to the east. And so as a consequence, the rift was eastward of the suture, leaving a remnant of Africa welded to North America. And when we look at a cross-section of North America, here we see the Appalachian Plateau, the Valley and Ridge mountain range. Here we see the Blue Ridge, the Piedmont. These are features that people that live on the east coast of the United States would recognize very quickly. And then there's a coastal plain that is a remnant of Africa. So next time you are in Florida, Florida, it turns out, is a remnant of Africa that's stuck to the eastern part of the United States. And it greatly expanded the width of North America, the North American geology. So the last example of collisional mountain belts that I want to talk about are the Cordillera, specifically the North American Cordillera. So Cordilleran type mountain building is associated largely with the Pacific Ocean. We actually see it extending well beyond North America. We see it all over the place. But this is where we believe we see kind of the classic examples that we can then use to extrapolate out to the rest of the world. And this is based upon the idea that it's highly likely that subduction zones that are occurring out in the middle of the ocean will form island arcs, which will eventually collide with continental crust. In other words, we're going to have these marauding islands, just like what we just described when we were talking about the formation of the Appalachian Mountains, the tectonic orogeny. That this is probably more common than we normally imagine. Just because we don't see it happening exactly today doesn't mean it hasn't happened repeatedly throughout Earth history. And so the collision and accretion of small slivers of continental crust form the mountainous regions that rim the Pacific. We see it everywhere. We see these terrains where we say, where in the world did this come from? This looks like it belongs out in the middle of the ocean, and yet here it is. And effectively, the question is, well, how did it get there? Why would it be there in North America? Why would there be these interesting terrains or these exotic accreted areas, say in a place like California? And the reason why is that during the breakup of Pangaea, in other words, when Africa was rifting away from North America during that breakup, the Farallon Plate, which is a plate that no longer exists, at least not off the coast of California anymore, because the San Andreas Fault is actually symbolic of the death of that plate. But the Farallon Plate began to subduct underneath North America. So there was an old subduction zone off of California. We talked about that a little bit earlier. And what would have happened from time to time, just as we described with the formation of the Appalachian Mountains, is you'd have an island arc that would come in and microcontinent behind it into a trench. And what would happen is the island arc would accrete. It would basically be scraped off and accreted to the continent. And it would widen the continent. And that would move the subduction zone out, right? It would transfer it to the other side. And so here we have this subduction zone that would break this off. This one is now moving in. And so that old subduction zone is here. And now it's transferred to this new location here. And so this is then going to collide in, and it's going to create another one. So the subduction zone is going to keep walking outside of each one of those terrains. And that's the idea of these Cordilleran type mountain building events, is that you form these giant mountains. They're not nearly as large as the Himalaya, or at least we don't think that they are, but they're still very, very large mountains. The Castle Crags in California, again, that image that I showed you at the beginning of the lecture, is considered an example of potentially how this might have happened, some of the terrains around that. So let's look at what these terrains are. And I've been using the term already. I kind of jumped the gun a little bit. But Cordilleran type mountain building, there's terrains are accreted blocks of the crust. So this is the things that are being stuck as things are slipping down into the mantle through subduction zones. It's leaving the terrains that formed out in the ocean basins behind. Consists of distinct and recognizable series of rocks and formations, has been transported and accreted by plate tectonic processes. And so when we look at the west coast of the United States, from the Franciscan, which is an area that is deformed by the accretion of terrains, we actually see these things that look like they are formed in ocean. So here's an oceanic terrain, something that seems to be formed out at sea, right? So some prior to accretion onto the continent, some terrains were microcontinents, similar to Madagascar, and other terrains were island arcs, similar to Japan. And so when we come out and we map these things, these terrains, they form these ribbons, just like the mountains themselves, as we were describing at the beginning of the lecture. They form these ribbons that are parallel to the coast. And so, or what would have been at that time parallel to the subduction zone, which was located off the coast. And when we look at cross sections of these features, it's pretty clear that this is related to events that are happening at sea. So here's a cross section that's happening in this case in Alaska. So this is the North American Craton is up over here. To give you an idea, the Great Alaskan Earthquake happened right here at this subduction zone. And so this would have been in an area located right through here. So here's Rangelia, the Yukon-Tanana terrain. All of these are located right in here. And so when we look at the cross section, here's the North American Craton, here's the Pacific Plate, and these are interpreted as a volcanic arc that happened here. and we have different types of terrains that accreted at different times. So, here's the Yukon Tanana terrain that would have accreted about 180 to 225 million years ago. And then that was later on underplated, and accreted next to it was this Rangelia terrain, which accreted about 85 to 110 million years ago. The Prince William terrain, 50 to 67 million years ago. And you can see it's all walking out. And each time this happens, it accretes a terrain. What happens is the subduction zone then transfers to the west in this case, or to the south. Is actually how this works. Because if we come in here, we can think of it as going into the southwest, I guess. All right. So then subduction continues, right? It just continues until another crustal fragment slams in, and it just keeps walking out. And you wind up with a series of structures just kind of like this. That's what we're seeing here. That's what these structures are. All right, so that's it for subduction zones. Well, nothing, it's never finished with subduction zones. There's always something playing a role with subduction zones, especially when it comes to mountains. But for the most part, that's the last time we're going to talk about subduction zones as being a direct cause for the formation of mountains. They can also be indirect. There's an indirect way that we can do this. We're going to show this here in a moment. Now, paradoxically, you can actually form mountains not through compression, but actually by pulling the mountains apart, or by pulling the continents apart through continental rifting. This is just kind of another way to do things. And we've actually mentioned this in a previous lecture when we talked about the formation of detachment faults, half-grabens and grabens, and you can form very large mountains, very tall mountains in this way. So continental rifting, it turns out, can produce uplift and the formation of mountain blocks called fault block mountains. And a great example of this are the Teton Mountains of Wyoming. So here's the Cathedral Group in the Teton Range. It's a huge mountain range. And what happened is a fault formed here, and what it did was it uplifted what was originally crystalline basement rock, the old batholith rocks, through extension. So as you're pulling these things apart, a normal fault ensues, and that normal fault then uplifts this basement rock here, and it down drops the valley rock. So here's Jackson Hole Valley, here's the Grand Teton Range here, and this is what you're seeing here, exposed, all these beautiful granites up in these tall peaks. This is not formed through collision, this is actually formed through extension, through pulling apart rocks. Another place where we see this extensively is in the Basin Range province of the western United States and northern Mexico. So the Basin Range province is one of the largest regions of fault block mountains anywhere on planet Earth, and they're very well studied. There's great universities, UCLA, many University of Arizona, that have all studied these areas extensively. And most geology students actually spend some time as young students studying in the Basin Range. They're located between the Sierra Nevada and the Rocky Mountains. So the Sierra Nevada is here. These are those batholiths that we were talking about earlier, the Andean style. And then here's the Basin Range province in the back. And then here we see the Rocky Mountains located up over here. It extends north-south roughly 3,000 kilometers, encompasses all of Nevada. So this is Nevada right here. Portions of surrounding states and a large portion of New Mexico. And these are pretty typical. These big, beautiful layers that are uplifting, not necessarily deforming complexly, though that can happen, but uplifted layers that are frequently rotated with a large fault system, basal fault system right here, that is allowing this half-graben to rotate its way up. It's a big, beautiful structure. And these are all mountains that are extended here. And so how do you get extension forming mountains that extend all the way from the Rocky Mountains all the way to Sierra Nevada? There's a couple of ideas for how to do that. Two major theories. The first one is that following the subduction of the Farallon plate, so back, over 30 million years ago, 40 million years ago, there was this old Farallon plate that was forming a subduction zone off of western North America. It was compressing and forming the Sierra Nevada batholith. It was creating the volcanoes, then the Four-Arc Basin, and all of this. And then what happened is we could see this geometry here. These points eventually came into contact with the subduction zone, and the subduction zone actually ran over the ridge. So here's the mid-ocean ridge between the Pacific Plate and the Farallon Plate. It ran it over. And so the result was the San Andreas Fault set up in between. And there's still a little bit of the Farallon Plate today. It's called the Juan de Fuca Plate up here in the Pacific Northwest, and that's what creates the Cascades. This is the volcanic system, or the roots of the volcanic system that produce Mount St. Helens and Mount Lassen, very active volcanoes that have erupted in the last 150 years. So following the subduction of the Farallon Plate, the northwest movement of the Pacific Plate produced tensional forces that have stretched the region. So let's look at these arrows here. Here's the Pacific Plate, it's pushing off to the northwest, the Farallon is going to the southeast, but once it touches, notice that the Pacific Plate is now going to the northwest, and this is very different than the compression that was happening under the Farallon Plate. And so the consequence of this could be that now that North America is not resisting this, it could even be pulling it or extending it some complicated way, that North America is then expanded, right? That western part is expanded. Another explanation is that 20 million years ago, the lower lithospheric mantle decoupled from the crust beneath the region. This is the idea here, is here we've got the Farallon, it's decoupling, and then that produces something called delamination. So that delamination, or that separation, then causes upwelling and lateral spreading of hot mantle rocks, producing tensional forces in the crust. So this is another way that you can do it. We actually don't, it might even be a combination. So, or even a third option we haven't considered. But those are the ideas for these tensional forces creating fault block mountains in North America. Now there is kind of a last topic we want to talk about for how you can get tall mountains. It's the principle of isostasy. So less dense crust, it turns out, floats on top of the denser rocks of the mantle. So you got crust up on top for a reason. It's because of density. Now, isostasy is the concept of floating crust in gravitational balance. So if you have a large amount of crust, it's going to have an effect on what's going on below it and around it. So it's going to imprint itself, much like a block of wood floating in water. So if you have a taller piece of wood floating in the water, it's going to have a deeper root. It's going to sink deeper. So while you have this tall mountain here, it's going to have a deeper imprint. Same thing here, right? If we have a tall mountain, it's going to have a deep crustal root that's going to extend and bend down the lithospheric mantle. It's going to be a very thick impression. And so this turns out is believed to have a major effect on how mountains grow and eventually how they die. It's a big part of how they die. So how is isostasy related to changes in elevation? Well, when you start to compress let's say two continental crusts, right? Or you've put some type of subduction zone over here, but you're compressing this and raising up a mountain range. What happens is that you're building up this mountain range, and just like this piece of wood that is floating up high, it's going to have a deeper root. In other words, it's going to have a major gravitational effect. It's going to push the mantle out of the way. The mantle is going to move as that root expands down into it. And then eventually, you're going to start having erosion. And so that erosion is going to start moving that material away. The mantle flow is going to come in. The isostatic uplift is going to happen. So as the mantle is coming and pushing back in at the base and eroding that root, it's going to lift the mountains back up, and then you get more erosion, more deposition off to the side. And so over time, what used to be a tall mountain will eventually get leveled off, and the root will then be restored to its original position, where it will be relatively flat across. So you'll see the ancestral old mountain remnant that's there, but we can imagine that this is something that was once very large. And so the process of establishing a new gravitational balance in response to loading or unloading is called isostatic adjustment. So the Appalachian Mountains are undergoing isostatic adjustment right now. This has also been happening in the in the Rocky Mountains, in the Himalaya, anywhere where you have large mountains and erosion is happening or even uplift is happening. It's either, in the case of the Himalaya, the mantle flow is moving out of the way because the mountains are still growing. But if the mountains are actually actively eroding very rapidly, the opposite is happening as erosion is carrying off. It's pulling the stuff off. And so the mountains are dying, and that is reversing the mantle flow and lifting the mountains up, which then feeds more erosion, right? As the mountains go up, the erosion then pulls it down. Okay. There is a point, though, where effectively things can get too high. You can get mountains too large. So as mountains grow, gravity acts on the warm and weak rocks inside of the mountains. So the mountains, we usually think of them as these brittle, strong rocks all the way up, but they're not. especially down at the roots, they could be metamorphic. They could be under very high pressures and very high temperatures, maybe not enough to melt them, but certainly enough to deform them ductily. And so if that happens, the gravitational forces will get so large that the rocks will actually flow laterally out. So imagine we have compressional stress coming from both sides on this diagram. We have uplift and subsidence, and then over time what will happen is these faults will develop, and the mountain, while it's built up high, because the base of it doesn't have the strength to be able to hold it that the crustal, the hard, brittle rocks can hold up in the top of the mountain, the ductile rocks will start to flow, form these normal faults, and you'll start seeing subsidence. Okay, and so this ductile spreading and consequential subsidence is referred to as gravitational collapse. So these mountains only get so large, and then effectively the rocks at the base start to fail. They can't take it. And so, there's a reason why there's only one Mount Everest, and it's a big difference between Mount Everest and what's happening over at K2. There's a 750-foot difference between the highest and second highest peaks. And then effectively, that's about as high as you're going to get mountains on Earth. The amount of erosion, you start having issues with metamorphism and ductile deformation out at the base of the mountains. And so the mountains start to fail. One other issue that we need to bring up, since we're bringing up the mantle, is raising the edges of these cratons up where ordinarily you wouldn't have a mountain. So for example, southern Africa, especially South Africa, where the country is actually at, and this is the escarpment in southern Africa that we see here that I'm going to be referencing, is way too high to be explained through any type of collision or rifting. There's nothing that makes any sense for it. And when we look at the information that we have on the mantle underneath Africa, one of the things we've discovered is that there's a super plume down there. And there's a super plume of hot mantle. This hot mantle is rising up underneath Africa, and this plume can elevate the entire region. And so this is the flat plateau of the craton. It's now been uplifted way up high. It's actually the platform that we see up there with the sedimentary rocks on there. And this portion of southern Africa is just extremely high, much higher than we would expect, about 1,500 meters higher than we would expect from a stable craton. So the mantles can just simply push up a mountain in that area just by putting a large amount of heat at that location. All right, so we've gotten all the way through it. Those are the main ways that we can form mountains. The geology of mountains is fascinating. It's complicated in some ways, but it's all related to the way that the mantle is interacting with the crust, and the crust is circulating and subducting and doing all of the things that it does. So mountains are just very large scars at the surface of the earth where the volcanoes form, where the rocks form and fold and deform in accommodation of the Earth's plate tectonics. Our next lecture is going to be on the death of mountains. This is basically landslides and mass wasting, the erosion processes that take mountains up high and bring them down. And the result of that is absolutely fascinating. And so we'll be looking at a lot of landslides, the way that rivers actually cut into these mountains. And it's actually a pretty exciting lecture thinking about how this stuff happens. So I hope you'll join me for that lecture. In the meantime, take care. Farewell.